expertise in the field of power systems, Dr. S. Selvakumar. His profound knowledge and vast experience promise to make this gathering a memorable and enriching one. We extend our warmest welcome to our esteemed resource person, Dr. Selvakumar, as well as the faculty members, students, and the participants. Ladies and gentlemen, it gives me honor to introduce our distinguished resource person, Dr. S. Selvakumar, a gold medalist in power systems from Anna University, Chennai. Dr. Selvakumar holds a bachelor degree in electrical and electronics engineering. He brings with him an impressive 18 years of experience in power systems studies, with having a reputed organization like ABB, TCE, PRDC, and Eventure Technologies. Since August 2019, he has been heading a team of power system engineers at Power Projects under, where under his capable leadership, the organization has successfully executed over 500 projects across 42 countries on 6 continents. Dr. S. Selvakumar expertise span a wide array of domains, including but not limited to flow studies, reactive power, compensation, voltage dip, and drop analysis, short circuit and transient studies, harmonic analysis, renewable energy integration, microgrid, and distributed generation solutions. Beyond his technical achievements, he is also celebrated in the industrial sector as a trainer in power system and protection. Furthermore, he serves as an associate editor for the journal Transaction on Engineering and Sciences and is an industrial expertise member in technical advisory committees of several academic institutions. We are indeed privileged to have such an eminent personality share his wisdom with us today. Please join me in giving a warm welcome to you. Over to you, sir.
And sir, I will be giving you the host rights to you, sir. Sir, you are a host now. Thank you, sir. The session is yours.
Thank you, sir. Thank you so much. And probably almost close to 50 people. So it's my pleasure and privilege to meet you probably on the screen. And like one thing to start with, I do not have 90 minutes. I have 80 minutes. Hope you are able to see me as well as hear me. I want to make this next 80 minutes most useful for you as well as me. So like means I expect quite a lot of energy in the room. And probably when we are talking about smart grids, renewables, integration, challenges, solutions, power system is the most dynamic system in the world. And we should be most dynamics to probably understand the dynamics of and most critical part of is renewable integrations. If you're super excited for the session for the next 79 minutes, just put yes, short form of super excited in chat and we will start. And I want the chats to be probably active for the entire session. That's where I can interact. I may not be able to allow you to unmute. If you're super excited for the session, just put yes, yes, super excited in chat. Yes. And at least like I have one more colleague from my end, like Kulali, she is super excited. So if others are super excited, so I expect some response that like we are super excited. Because this next 80 odd minutes, like we are going to learn quite a lot of things. Probably all the things from the internet. All the things what I'm going to talk is not something which is hidden potential. No, it's open to the public. If you just open our eyes, what we can see in front of our eyes is what I'm going to talk about. So let's get started. And if you have any questions, feel free to post the questions in the chat. Like means if you feel the questions are needed in between, like maybe after 30 minutes, we can take up a Q&A for 10 minutes. Then next 30 minutes, then we can take up a 5 minutes Q&A. But if you have any questions in between, use the chat box, post the questions. I will be happy to answer. And the smartness comes when the interaction starts, right? Like I mean, so say it's not the I'm going to keep talking for the next 80 minutes. No. When we talk about smart is intelligence on both sides, having the right channel and the right language to communicate. So ensure that you are using the chat box effectively. That's my request. So with that, let's straight away get started. Let me jump into the slides. If you're able to see my slides, let me know in the chat. Just with SEE, so that I know that you're able to see my slides. Integration of renewable energy sources in smart grids. If you're able to see my screen, are you able to? Yes, that's great. Perfect. All right, good. So, integration of renewable energy. So, this is my what I have planned. Renewable energy status as on today, or why this topic? That's like always why. That comes first. Where we are standing today, why it is not easy, what are the challenges, and probably how to give probably the solutions. As an academician, like what you will get out of it. So that's pretty much, I mean, to say on the commercial sense, which we can talk. We can talk at the beginning. So, means to say now, probably we are talking about NBA, like many other stuffs, NAAC, right? Like ranking, etc., etc. Everywhere, this funded projects people are talking about. Easiest way, easiest way to get a funded projects is probably in this sector. Grid compliance study. That's pretty much I'm going to talk about. Just to give a fact, for a simple grid compliance study projects, Siemens charge about like 50 lakh. We are not that brand, like we charge about like 25, 30 lakh. And probably like if you charge like say 10, 15 lakh, like there are infinite projects in Indian market. I'm not talking like the global market. I'm just talking about an Indian market. There are infinite independent power producers. Those who are willing to put up a solar plants or a wind farms or a hybrid plants are struggling to find out the right consulting organizations where I believe like the academic institutions can give an easy solutions. Which means for each and every 200, 300 megawatt projects, getting a 15 lakh is an easy job because to an extent, like as I told, like Siemens is charging about 50L and probably we are charging about 25 to 30. Still, like I mean, so we are getting like abundant of projects. And probably like if you get like if you adjust the demand 10, 50, why not? Like you will get a projects. And there are quite a lot of independent power producers in India, and probably the challenge is going to grow. And probably like if you're looking really something kind of stuffs, you can do real-time projects, which makes money, which gives some satisfaction, which helps you to implement what you have learned in your UG or a PG or your PhD. Right? Like that's essentially what we are going to talk about today. So just to understand that, let's talk about the first topic. Where we stand today, renewable energy status as on today, why renewable integration is not easy, what are the challenges. We will go through the grid compliance study, like means we will go through the grid code of India. Like means if I am trying to connect a wind turbine generator, if I am trying to connect a solar plants, like what is necessary as per the grid? What are the things which you need to fulfill? So we will see. And then probably like we'll discuss some solutions and discussions. With that, like I'm leaving just to give an idea, like any guess, like what's the installed capacity of power plants, total installed capacity in India? What is our total installed capacity? And like I'm trying to find out or figure it out how much renewable percentage which we have. So that's my next question. But let's try to answer the first question. What's the total installed capacity in India as such? What's the total installed capacity? Any guess? How much megawatt or a kilowatt is the total generation installed capacity which we have? And probably like means it's really absolute important to understand this question because any country's growth is measured by a term called per capita consumption. Like I mean to say, how much electricity is consumed by the individuals that measures or that gives the quality of the country in terms of anything, even then better than GDP, right? Any idea? Like any guess? So maybe I will put probably one level question below, like How many of you belongs to electrical department? If you belongs to electrical department, just put E in chat. If not, like different branch, just put N in chat so that I know out of 58 people whom I am addressing to right audience, or probably like if it's a different branch, like I can slightly change or like touch what it is needed. Yeah, thank you, Rini, for just confirming that you are from Triple E. Others, 58 people, at least I get like 30 responses. Sandhya from Triple E, that's great. Devi from Triple E, that's great. What about others? Kanagraj from Triple E, Dr. Srinivasan from Triple E, that's great. So like I expect the chats to puzzle. Like when we are doing a free webinar, I expect the chats to fly. Yeah, cool. Yeah, I know. Unless you are from Power Projects, right? Well, yeah. Others, can you just like if you're not Triple E, that's fine. Like I mean to say, you put a branch or just put no in chat so that I know. Like means to say who is the audience whom I am interacting with. Yeah. All right, that's great. Like that gives a fair idea. Then, like, I mean, so far nobody has told like different things. So I'm presuming predominant of the audience, not all of the audience, at least predominant of the audience are from Tripoli. And just to answer the question, what's the total installed capacity and how much percentage renewables? I'm just casually going ahead with Google, and I'm searching a terminology called the CEA, Central Electricity Authority. So when I search the CEA, I can straight away land in the page install the capacity report, which you want. Yes, you can. Or else, like if you want to go to home page and find it out where is the install the capacity, that's always a better way of doing it. I recommend that also. If you probably visit CEA website, homepage itself gives some beautiful informations. Indian power sector performance during October 2024. Do not ask me November. November data, they will update it another 10 days, right? Like generally, they will update it before 15th of next month for the past month. So this is Indian power sector performance of October 2024. We'll come to that little late. But let's try to answer our first question. Like means what say report, go to monthly report, go to install the capacity, and then probably like means say you can download it in Excel or download it in PDF or view in PDF. Choices is yours. So this is 31/10/2024, which essentially mean about like 35 days old data. It's just 35 days old data. And like what I'm just trying to do, like I'm opening this document just because like I have already downloaded it. It's one and the same. Like don't think like I have used a different document. So this document and like what in PDF which I have opened is one and the same document. So if you look at 31/10/2024, that is 31st October 2024, our total installed capacity is 454 gigawatt or 4,54,452 megawatt. This is a grand total. They have given region wise north, west, south, east, northeast islands. They have given ownership wise state, private, central, state utility, private utility, centrals, say Adani, Reliance, etc. private. Tamil Nadu Electricity Board, that's probably state. Central, maybe NTPC, NLC, it probably comes under central. So means to say they have given like coal, lignite, gas, diesel. So split up again, they have given coal, lignite, gas, diesel, nuclear, renewables, of course, hydro, renewables as a part of ministry and ministry for new and renewable energy. So, and this total, cumulative total they have given. So total installed capacity is 4,54,452 megawatt. So I'm just making an Excel sheet and I'm just trying to keep this number 454.452. Let me probably try to keep this number in gigawatt so that it is easy to remember. 454 gigawatt or 455 gigawatt is what's the total installed capacity in India. And if you look at what is being classified as a renewable energy under Ministry of New and Renewable Energy, It is about like 156.247 megawatts. 156.27 gigawatt, sorry, 156.247 gigawatt or 1,56,000 megawatt. If you look at renewable percentage today, what we have as an installed capacity, we have an installed capacity of renewables about 34.3 percentage. So what's it mean? In India, in the total installed capacity, the renewables accounts for about like 34 percentage. This renewable includes small hydro, wind, bio, and solar. And out of which, like, look at solar, how much it is, which is predominant renewable, 92.119 gigawatt, 92,000 megawatt. If you look at in the total installed capacity, solar alone contributes to about 20.27 percentage. Right. So what is the percentage of the solar in the installed capacity? Like means was it 20.27 percentage. Why I am talking all these things? Why I am talking all these things? There is a reason behind why we are talking about. When we talk about renewable integration, why we are talking about a renewable integration? When I have started my career in 2006, nobody have cared about renewable integrations. Nobody has asked what is the renewable integrations. Nobody has talked about grid compliance studies. Nobody has talked about energy storage. Nobody has even bothered about a grid code. Nobody worried about like how to model wind turbine generator or a solar emitter. It's scenario of 2006. Still, I remember first grid compliance study. I should not call it a grid compliance study. I have done a power evacuation study for a wind farm, where I have modeled a wind turbine generator as a negative load. I have modeled a wind turbine generator as a negative load. Report is approved by Central Electricity Authority about 18 years back. Definitely not today. Why? By the time this renewable fraction is not even 3.4 percentage. Now it is 34 percentage. When the renewable is like in a single digit, you do not really have any problem. If your renewable percentage is in a single digit, you will not really have any challenge. But if it grows to 2 digit, like let me put this renewable, if it is 0 to 10 percentage, neither storage nor control is required. If your renewable is like so say 0 to 10 percentage. If it is 10 percentage to 20 percentage, then you don't need a storage, but definitely you need a control. Control is required. Control is required. If you have gone beyond 20 percentage, you need a storage as well as control. And 2006, when I have started, like we have never worried about modeling, we never worried about a control, we never worried about a storage because it's about 3 percentage. Why we are worrying? We are not 20 percentage, we are already in 34 percentage, and we are trying to probably go much faster and probably cross 50 percentage in probably 3-4 years to come. Right. And beauty is like in a total installed capacity, solar alone accounts for about 20.27 percentage. Like to say, why we are talking about only renewables? Is there any problem with the renewables? Let's go to our slides and probably talk a little more. But at least I have given a renewable energy status as on today. This is total installed capacity of 454 gigawatt. 156 gigawatt comes from renewables, out of which 92 gigawatt comes from solar and probably about 47 gigawatt comes from wind. And the link which I have probably put it in the slides also. When the slide reach you, like you will be able to get the same document in the link, like what you have, like you can pretty much, I mean, to say, take this. So it's a public data which is available. But like means to say, most importantly, like we need to ask a further question. Okay, renewable is growing, percentage is growing. So what? So what comes in the next slide? Why we have gone for renewables? People will think that it is like, I mean, what to say, it's because of environment. This is because of a climate change. Because people are genuinely believing in environment, etc., etc. That's not really the reason. Renewable energy is cheaper than any other form of energy. That is today. Please make a note of the statement. If somebody is thinking that, like, I mean to say, we are installing wind, solar just because we care for the environment, that's not the reality. That's not the true. Independent power producers, those who have money, are not really environmental peoples, are caring about environmental, because the same people, those who run probably other industries which is going to pollute the world. Why the world is focusing renewable energy today is because of a cheap, because it is economical. That's the first reason why we are looking at renewables. Of course, environment may be a second factor, definitely not the first factor. Just to give an idea, cost of energy comes from solar is extremely cheaper. Global best benchmark price which we have at the large scale solar plants is 1 unit you can generate at a price of rupees, maybe one rupee 5 paise. Let me repeat my statement. Like means to say, there are bids which has happened globally. Those who are able to compete and probably produce the energy at like rupees 1 p 5 paise. And even if you look at like recently concluded quite a lot of solar energy corporation, SECI, right? Like if you're not really aware of, like you have to be aware of this. Yes, ECA, SECI, right? Like I will be throwing quite a lot of information, so it's your responsibility to catch it up. So SECI, they have floated quite a lot of means to say tenders for a solar plants in a market at the moment, like means to say solar plant, they're competing at a price of like 2 rupee 30 paise, 2 rupee 40 paise, at max 2 rupee 50 paise, not more than that. Which means even for 300 megawatt, like means to say you will be able to invest capital investment, and you will be selling this energy for 2 rupee 50 paise for the next 25 years. Still, the peoples, those are putting the money, about approximately 4 crore per megawatt in solar plant, believe that they will be able to take back that money. And probably the people those who are dumping money are not really idiots, they are smart. So they are putting money 4 crore per megawatt in solar plant, because they know they will be able to extract that money. And just to give an idea, like means to say, compare the cost of energy from the other sources. Thermal, it is definitely at the price of about 4 rupees per unit now, compared to 2.5 rupees of solar. And like if you take maybe a diesel, it's 20 rupees, 15 to 20 rupees bare minimum. Gas, again in India, it is definitely expensive, like 8 rupees or more. So like means to say, solar, why it is growing, why it is continue to grow? It continue to grow because it is the cheapest form of the energy which is available right now in front of us. If that's clear, just put CC in chat. CC stands for crystal clear for us. If that's clear, just put CC crystal clear in chat, and then like I mean, so we will move forward. Yeah. Yep. Shall I get few more crystal clears? Yeah. All right. Yeah. Thanks, Sandhya. Thanks, Jikish. So let's jump on to the next point. It is cheap, it is environment, it is climate change, beautiful, but like why adding this renewable integration is not easy? Why it is challenge? Why it is difficult? Like 30 years back, just 3 decades back, 1990s, loads are variable in nature in power systems. Your thermal power plant or your hydro plant or your gas plants or your combined cycle plants or your nuclear plants are controllable. So load is the only factor which is continuously changing with respect to time, and you will be having a governor in your generators. And whenever there is a change in demand, the frequency will change and the governing system will govern. The problem has solved. It's 3 decades back when the renewable integration is 0% or probably in a single digit. Now we have probably we seen like we are approaching 35%. So like now load is not the only thing which is variable. My source which is also uncontrollable. Wind I cannot dictate, means you have to generate this much energy this time. No, it's not possible. It's probably only when wind blows, when wind is available, you can probably generate. Similarly, like means the solar you cannot control it. When irradiation is available, you will be able to generate. Irradiation is not there, you will never be able to generate. So previously only the load is changing and the generators are controlling. Now, as a part of the generator, there are about 35% of the sources comes from renewables, which becomes uncontrollable. So this adds the complexity in the equation. Previously, load is uncontrollable, sources are controllable. Now, loads are absolutely not controllable. In generation, 35% of renewable energy which we have added are not controllable, which means the power system engineer, the biggest challenge is how I am going to balance the generation and demand at each and every moment. Right. That's going to be a biggest challenge. And like means, so why do we need to balance the generation and demand? If you are not balancing the generation and demand, then like I mean to say, what will happen? Your frequency will change and may results in collapse as well. So maybe I'm just giving you some thoughts for you to probably read it. Like I'm not really going to, I mean, should say, take it further on this topic. I leave it to you to, I mean, so to say, do it. Probably, if you're not really aware of our YouTube channel, this is our YouTube channel. So that's the link where I have talked about if there is a difference between the generation and demand, what will happen to the grid, which I have talked about. So you can go through. That's a beautiful video to go through, right? Probably like do not miss out this YouTube channel as well if you're an electrical engineering faculty, and probably like pass this informations to your college students as well, because how power factor which we have studied in our college probably have an impact on the commercial. Probably some basics like power factor correction we have covered in detail. Right. So moving further, it is generation load balancing and the stability. Previously, when I have a conventional generation like thermal, hydro, nuclear, I have something called inertia. I have stored some kinetic energy in my rotating devices. But with the growth of inverter based renewables, IBR, which we call, so we do not have inertia, we do not storing any kinetic energy. Any disturbance in the system, like means my system is gone for a toss. So that's essentially like, I mean, should say what is being probably look at as a stability perspective. And spinning reserve, obviously we need to maintain additional spinning reserve because wind or solar is uncontrollable. And power quality is another challenge. When you are going with an inverter based renewable resources, this injects harmonics to the system, this injects a DC to the systems, this probably introduces a flicker in the system. So all those things which you need to probably look into. So what's the document which I'm going to share next is what you need to understand if you want to connect the solar plant or wind farms into Indian grid. This becomes mandatory now. If you want to connect any wind farm or a solar plant, it is essential, like you need to obey this like 23-page document, which is mandate, which is of course probably like I mean to say working group from CA, Central Electricity Authority, CTU, Central Transmission Utility, OSACO, SECI, like I mean to say it has done long back, and probably like now we have a beautiful grid compliance document, part 1, part 2, part 3. So let's look at like because of a time constraint, I'm going to share this document. You can go through, but like let's straight away jump into part 3. Right. What like means to say one the first study which you need to do when you are probably from an academic institutions, you can try this as well. So means what say if an independent power producer is putting up a solar plant and connecting to transmission utility, which either be owned by central or by a state, then like means so you need to follow or you have to do this. Power quality, which is harmonics, DC current injection, and flicker. So this you need to probably do in a software called PSCAD. If you are aware of the software PSCAD, just put PSCAD in chat. If not, no worries. I will come to that. If you're aware of the software called PSCAD, can you just put PSCAD in chat? If you're not aware of the software, just put no in chat. So that gives me a feel that like how many of you are aware of the software. So when you're putting that in chat, like let me go to the next point. Reactive power capability test. This is how much reactive power this wind turbine generators or solar inverters or battery energy storage systems should meet. Voltage right through. This is high voltage right through, low voltage right through. Frequency response. If the frequency is changing in the grid, how this wind turbine generator or solar inverter has to behave. Active power control set point. Ramping capability test. So they have given like this one page is good enough. Like if you're not able to go through this 23 pages, go through this 11 pages. This gives you like if you want to connect a solar plant or a wind farm to Indian grid, what are the tests which you need to do? Power quality you have to do using detailed EMT model. Reactive power assessment carried out in a detailed RMS and equivalent EMT model. Detailed RMS model and equivalent EMT model. And the rest of the things like voltage right through, frequency response, active power, ramping, all those things. This has to be carried out by both RMS as well as EMT, but it's an equivalent model. So if you just aware of this, and like means to say, what's the condition for a power quality like harmonics, what you need to meet, for a DC injection, what you need to meet, and flicker, what you need to meet, reactive power capability, what you need to meet at various grid voltages, and like for frequency response right through, if you just aware of all these things, then probably like means to say this like means to say you will be able to do probably this grid compliance studies. And like means to say there are two simulation softwares which is needed. So if you're not aware of the softwares, just make a note of both the softwares. One is PSCAD, that's EMT2, which I'm putting it again in the chat. Second one, PSSE, that is like, I mean, RMS tool. Right. These are all the two tools which just you have to be aware of. And like means to say, beauty is for an academicians, both the tools you will be able to get a free version of the software. Right. PSCAD, student license or a faculty license, which you can get it for free. Of course, it has a limitation of 40 nodes. PSSE, you can find it out like a student version up to 50 bus system free, which you can try. And like with the 50 bus system, you will be able to do quite a lot of studies on PSSE. Right. So I'm not really going to promote these two softwares because like we have all the simulation softwares, other softwares as well. And why I talked about this, because if you want to do the renewable integration in India, this is the only two softwares which we do not have any other options. Right. Now let's move on to the next. What are the challenges? One challenge which we have talked about here, why it is not easy. Let's look at like the other challenge as well. So we have talked about like means to say we have 455 gigawatt installed capacity, out of which like means to say something on the renewables and like accounts for 35%. Solar is about 20%. Beautiful Excel which we have worked around, right? So this is only the installed capacity perspective, not the energy perspective. So this is power perspective. There is a different dimension for it. That is energy perspective. Let's look at this energy perspective. And like for this, like you need not really go anywhere. Where you have to go is like you have to go to like CA homepage. That's all. That's simple. What I have in the slide is exactly this. If you look at October, they have not added any conventional capacity, thermal, hydro, nuclear. No, they have not added anything. But if you look at renewables, they have added about 1,700 megawatts. Transmission line, they have added 1,454 kilometers. Transformer capacity, they have added. And this is what you need to probably look into. Conventional generation is about 108 billion unit. Renewable is 30 billion unit. Energy supplied is 141 billion units. And the peak demand which is met is 219.22 megawatt. Coming back, this is installed capacity. But look at peak demand. Peak demand is 219.22 gigawatt. So which means I have an installed capacity of 454. Peak demand itself just merely about like 48% of my total installed capacity. My peak demand is just about 48% of my total installed capacity. So which means like we have sufficient spinning reserve. And probably 2010 power cut, serious concern for India. We are no longer a power deficit country. Like means our peak demand itself only 50% of installed capacity. We have sufficient installed base. Right? But let's look at the energy perspective only for the month of October. Conventional generations 108 billion units. Renewable 30.18 billion units. Unit you might be aware, 1 kilowatt hour. Billion, you know how many zeros. I do not know, so I'm not really going to talk about how many zeros which you have for a billion. Maybe use Google, that will give you. So this is conventional. This is renewable. And if you look at the renewable percentage in terms of energy in the month of October, which is about 20%. Though installed capacity is 34%, and generation perspective, it is 20.367%. And probably this can go slightly higher, probably during wind seasons, etc. Right. But at the moment, like if you look at October, this is a percentage of energy. So what's it mean? We are spending probably the electricity for this webinar, though it is not a physical webinar, but we are like means wasting some energy. That's the right terminology. Wasting electrical energy. That means like we may be using light, we may be using laptop, we may be using mobiles, and probably attending this webinar. So which means we are consuming electricity. If we had this webinar in the month of October, means to say we are talking about renewable energy, green energy, but that webinar consumes 80% of the energy which is spent coming from the conventional like coal or like lignite or a diesel, probably that pollutes the world, right? probably like me to say come back and see in the month of January, like how much percentage energy for this free webinar probably comes from the renewables. Like at least this has grown to an extent, great extent, 20%. So India is to an extent renewable. We are a top-notch player, having close to 35% installed capacity, and already we are making 20% of the energy from renewables. And probably like if you want to meet 50% of energy from renewables, 50% of the energy from renewables, then like means to say we have to install a huge renewable capacity, because we might be aware for a simple fact, solar will not generate the power during non-solar hours, which is night. And probably like me to say you have to probably put up a solar plant, store the energy somewhere, and then probably I mean to say supply that during night hours. That's how probably like you will be able to increase the energy which is met from renewables. You will never be able to probably increase this percentage without having some proper energy storage solutions. And probably you might be a thermal plant or uh, gas plant. It takes its own time to start and probably shut down, right? Like you cannot start just like that and probably start generating electricity, because it's not a powertronics which operates in megahertz, right? If you probably put up a thermal plant off, it takes days to start. If you put up a gas plant off, it will take minutes to start. So it's not like just like that we start and ramp up, right? All right. If so far so clear, just put CC in chat, and probably like I have already opened this document and I have shown like what is the grid compliance study is. Maybe we will go for some other interesting facts. What makes our system complex? Something like solar eclipse event. But before that, like I mentioned, anyway, the slides which I am going to share it with you. And these are all general public links. I am not using any proprietary material of our organization or somebody else. It's all public domain informations. Right. Yeah, before jumping in, like if you have any questions or if you want to unmute yourself, let me know. I guess like we are about like 40 minutes from the beginning of the session. If you have any questions, unmute yourself or post questions in the chat. We will take up the questions and then we will move forward. Any questions? If there is no questions, just put no in chat. Like we will continue our session. If there is no questions, just put no in chat. That's absolutely fine. So I get some answers. No questions. Thank you, Sandhya. Others, I guess like 73 on board selected. Yeah, thank you, Kumar-san. All right, which means like it's good to go. Yeah, thanks, Priya. And like, the answers, like response which I have expected is better. Like that's what I have to say. All right, so let's jump into the topic. Let's talk about one event. Why this renewable integration is not easy. There's a solar eclipse event which has happened on 21st June. Like means I'm not really going to like means to give you the document, but I will give you the link itself, which I have opened it already. So I will directly go to this. Right. So this gives you an idea, like means to say from where I have taken this report. That's taken from the POSAPO. Right. It's a solar eclipse event on 21st June 2020. Why it is important? Like now already we have installed almost close to 100 gigawatts solar. But 2020, our installed base is like I mean to say, you can see how much is the installed base, right? Let's check like how much is the installed capacity of solar. Like I will go to some map. Yeah, this is probably giving some map on June 2020. We were talking about just about 155 gigawatt. We're talking just about 155 gigawatt. But like you might have noticed, like means to say we are already 220 gigawatt is our uh, demand which we are meeting, 220 gigawatt. Whereas like just 4 years back it is only 155. Just try to understand the speed at which we are growing. And let's look at solar. Yes, it's a typical solar generation in June 2019. This is June 2019, right? So average of 5 to 6 clear sky days, like means up to 5:50 in the morning, power generation is 0. After that, the generation increases. You can see this yellow line, right? Some oscillations. It's kind of a smooth one, right? Average of like 5th June to 20th June, and average of 5 to 6 cloudy days, the oscillation is a bit more. Why this all we are discussing? Because this event has happened. The solar eclipse event is happening on 21st June 2020. So we need to understand what could be the difference between the a normal day versus solar eclipse. So hope you know what is solar eclipse, right? If you know, just put K in OW. If you don't know, just put DK. Don't know in chat. So let's so if you do not know, this is solar eclipse. When moon passes between the earth and sun, blocking the sun's view from the small part of the earth. Right? It happens in the daytime, means then probably like means the irradiations will not reach that area, right? I guess like people know about it. That's great. So which essentially mean like I need not really spend time. All right, coming back. Look at how it happens on solar eclipse day. Yes. This is the data. 20th June, like it is 9 to 3 o'clock data. Look at this. Smoothly has increased and probably like perfectly close. But the next day, which is a green one, its solar eclipse starts here and probably power starts falling. And you can look at the mismatch. You can look at this mismatch. You can look at this mismatch. And probably you can see. Right. So solar obviously falls when there is a solar eclipse. And this is when like means to say solar installed capacity by the time I guess like is much less actually. Let's look at like how much is the solar installed capacity. I guess like by the time they have not given. So then like what we will do, we will try to find out what's the installed capacity in June 2020. So for that, like I'm again going for report, monthly report, sorry, report, monthly report. My goodness. Okay. Report, monthly report, installed capacity. So I'm just 2020 June. Let's probably look at what's the installed capacity. June 2020. You have a data. These are all the public data which I am opening. I am not opening something as hidden secret of somebody. 2020 June, exactly this report where it is. By the time, what's the solar installed capacity? The solar installed capacity is 35,000 megawatts. And today, what is the installed capacity? Today, the installed capacity is 92,000. So it has been tripled. Just look at this 35,000 to 92,000. Why probably renewable integration is important? Because even during the COVID and second wave was to hit all these things, and probably like I mean to say, solar is growing. Like I mean to say, it has grown 3 times in probably like about 3-4 years, which essentially means like they're growing at like much faster pace, right? So it's the reason why we are talking. So now, like means to say, 2020, when we have only 35 gigawatt solar, we have a problem on the day of solar eclipse, which is pretty much what we are talking or what we are discussing. Now, like if it is 100 gigawatt now, and probably aiming for 200 gigawatt in near future. Imagine if there is a solar eclipse in future, which nobody can prevent, what will have an impact on probably the grid? Who will be going to manage this mismatch between the normal day versus a solar eclipse day, right? So that's going to be like extremely, I mean, to say challenging. So this is also one reason like why we need to focus little more on like means the renewable integration, not just probably something something casual, right? All right, I guess like this report gives you more details. Like I'm not really going to talk much on. If not, share this link again. Early, like I will share it here also. You can probably pick it up. So now let's go to the next topic. Uh, like I'm not really going depth on this grid connected for wind and solar plants. That link is there. Some beautiful presentation is there. That could be the start of point. But let's take one simple example of like I mean, say wind farm of say example 800 megawatt or 1000 megawatt or 1200 megawatt. One of the 1200 megawatt solar plant which we are working on, that's a 1200 megawatt solar plant, like which we are at the moment working in Rajasthan. 1200 megawatt solar plant in Rajasthan, which we have recently done the grid complaint studies, and then probably maybe if you are in a stocks, SaaS, if you're investing, then like you may be aware this recently came in to IPO as well, right? So Lakshmi Solar, like means 1200 megawatt, like means to say in Rajasthan, which they have probably installed in multiple places, right? So they have backed this 1200 megawatt, and like means it has been installed and commissioned. So like a report of under construction renewable projects, which you can see, like means they have started in 2022, 1200 megawatt ISTS ranked like means to say projects, that is like means to say for an IPP, right? And like means to say why I am stressing all these things, because means to say one simple solar inverter can inject a harmonics to the system. A simple solar inverter can inject a harmonics to the system, and this can be amplified by your reactive power compensation devices, which is available in the system, and that can be threat for the entire country itself. So, like I'm just trying to introduce an third software, ETAP. I guess like I have introduced you two softwares already. One is PSCAD and other one is PSSE. I will introduce the third software, ETAP, and just to give a figure like what is on the harmonics. So if you're aware of the software ETAP, just put ETAP in chat. If not, just put no in chat. This also you will get like demo system, demo software. All right. Thanks, Satya. At least few people are aware of the software. Let's this comes in. So just to give an idea, like I mean to say if you're putting it up some transmission lines for evacuating the power, then like even if you inject maybe a small harmonics by the solar inverters, that can be amplified by the system. So let's take like means I am expecting like 220 kV transmission line, which probably carries a 300 megawatt power, which is generated by a solar plant. I am taking some short circuit current. Right. Let me assume the transmission line. I have just assumed the transmission line, right? And probably like here, like what you have studied in transmission distribution subject, if you're in triple E, like I mean to say, for the given conductor, given earth wire, given the configuration, whether it's a horizontal configurations or a vertical configurations or triangular configurations, and for the given number of ground wires, the software automatically calculates the line parameters. How it is related to renewables? So this system, the system like is probably connected with quite a lot of small solar inverters. So if you talk about like 3.3 megawatt central inverter, then like you will be having 96 inverters. If you're talking about like 300, if you're talking about 300 kilowatt string inverter, then like you will be having, means to say 960 inverters, right, to meet this 300 megawatt solar. So, like if you're injecting a small harmonics current here by solar inverter, that will be amplified by this transmission line capacitance. This is nominal pi model, what you probably talk about, like that. That's probably like I mean, so amplifies that harmonics. It amplifies that harmonics. So the outcome, like means to say, when your solar plant starts and probably start generating power, huge harmonics may come, and that may result in, like I mean to say, the voltage which is extremely beyond acceptable range. Let's just run a harmonic analysis just to showcase what could be the impact of this. What could be the impact of this lines and harmonics? So here you can see there is something harmonics, right? This can go like 17th order. This can go 75,313 ohms, which means even if you're injecting like 1 amps current, then that will result in a like extremely huge non-sinusoidal voltage. Let's probably run and then probably like let me show you like how the sinusoidal voltage looks like. Like the voltage sinusoidal, the waveform is beautiful because like so far like I mean so say we have not really injected any harmonics or something. Like if I'm trying to add some harmonic source here, what I'm just trying to do, I'm just trying to add a transformer, maybe 220 by 33 kV. I'm not really going to model up to the solar inverters because of a time constraint, but at least when I model, say example, 150 MVA transformer, and like means to say, for that, like if I give some harmonics, and then if I am probably performing the same harmonic analysis, previously that was beautiful sine wave. Let's see now, like means to say, how this waveform looks like. Is it not horrible? Harmonics is like 800% ish. It is extremely like compared like previously how beautiful the sinusoidal waveform was, and now look at like how badly it is oscillating. And probably this are all something which we need to take care, during the design. That's where this grid compliance studies or grid connectivity studies comes into picture and adds a solution. So go to this India grid compliance study requirements. You perform power quality studies, and like power quality harmonics exceeds the limit or something, then recommend necessary filters, or probably change something else, or probably modify the line length, or probably add parallel circuits, do whatever you want to eliminate harmonics. So these are all something which you can try, and like maybe uh, one of the video which we have given in our YouTube, maybe much interesting to watch. Let me check like whether we have that video. Yes, think so.
What if I told you can erase negative thoughts, overthinking, and childhood trauma permanently from your life by
Yes. So here, I guess it's not solar plant, but it's an industrial power system. So you have like 20 MVA load, which has 18.9 percentage voltage harmonic distortion and 40 percentage current harmonic distortion. Like, but if the load is lagging power factor, and if you're adding a capacitor bank to improve the power factor, instead of improving the power factor, it destroys the power quality. You can look at 18.9 percentage THD becomes 40 percentage THD, and the current 40 percentage THD has increased to 108 percentage THD. 40 percentage has increased to 108 percentage. And then probably like you can use this capacitor itself as a filter by means of adding a series reactors, etc. That has been explained in that video. Why these videos are must? Because most of the time we think, like I mean to say, we need some rocket science to solve some problems, but we may find solutions in much smaller, much the problems are like much simpler than what we think. One of the example, if you are asking like what should be the current in I, what should be the current total current I, when the current I1 in the branch 1 and the current I2 in the branch 2 are 4 amps and 3 amps respectively. Blindly we will answer this question as 7 amps. Some people will try to answer this as a 5 amps. Both of that are not right. Both of that are not right. It's neither 7 amps nor 5 amps. So what's the right answer for this question is probably like means what we need to look into when we are defining something on the power factor. So I'm not really going to answer this question. Probably like you can go through this video and then probably try to find out like I mean to say what is right and how it is related to the harmonics as well, and why power factor should not be defined as cosine angle between voltage and current. You will get to know from that video. So maybe moving further, like one last report which I need to probably thought of sharing is this one. Yes, that's it's a 443 page other big report. It is 443 page other big report. So when we are talking about Pan India Light Up event, so it is our Honorable Prime Minister called to switch off the lights for 9 minutes at 9 p.m. on 5th April 2020. 5th April is my birthday, and probably like I mean to say I have done a video on the 5th April 2020 at morning 11 a.m. about like 10 hours ahead of this event. So ensure that you are going through that video to get like much better insights. But like one thing is very clear, means to say grid system is to an extent stable despite of we are losing about 30 gigawatt or 30,000 megawatt in a short span of about 5 minutes or 10 minutes. Let's go, like I'm just focusing on only the some graphs so that like you can get some clarity or a picture. Yes, it is. So 4th April, that is on Saturday, that's on green color. Red one is 5th April, that is Sunday. They're plotting the graph from 8:30 to 9:30 in the evening. So Sunday, the demand starts slightly less than the previous day. So means to say people started switching off something well ahead of 9, and you can look at the demand of 115 gigawatt even falls to 85 gigawatts. But like the system is able to maintain the frequency and voltage without a challenge. How that is possible? That needs probably quite a lot of flexibility in the controllable sources, which all may not come from thermal. Predominantly hydro has supported, but in a long run, if we are able to do this event today, then it might be much challenging, because by the time the demand is 115 gigawatt, but like now what's the demand which we have talked about is 220 gigawatt. Our demand, this the peak demand has doubled, right? So like I mean, so if you are doing this now, and probably if you're probably there's sudden power drops by like about 25%, so we will be gone. Like means so we need very strong grid integration systems. All right, keeping 15 more minutes left with me. Is there any specific questions? If you want to unmute yourself or something, you can post it. I'm happy to continue my session, but like means I want to probably take up some questions if there is any. Any questions? If there is no questions, I can use next 16 minutes for my session directly. If there is any questions, post it, or if you want to unmute yourself to ask these questions, like means you can raise the hand or probably unmute yourself and post the questions. If not, like I can take my next 16 minutes for granted and probably I can go ahead. If there is no questions, just put NQ, no questions in chat. If there is no questions. Okay. I don't know how to properly understand the audience. All right. So let me go ahead and then probably yeah. Thank you, Priya. At least one. No, that's great. All right. So let's talk about like next 15 minutes. Maybe going a bit more on like means what say what we need to do on power quality, right? Or like means what say the renewable integrations, etc. And like we can touch a little bit of others topics as well. Like I mean, so see on the just give me a second. I will probably pick it up. What we need to focus. Yes. So as a part of grid compliance study, the first topic which you need to focus is power quality. So this is a power quality. First, harmonics, DC current injection, flicker. Three things which you need to do. Harmonics, you have to follow the standard IEEE 519. You have to follow the standard IEEE 519. And IEEE 519 gives the limits for the voltage as well as the current harmonics, how much it can be injected to the grid to various voltage levels. Let me open IEEE 509 document as well. So the latest document of IEEE 519. Yes, like yes. So this IEEE 509 2022, this gives the voltage limits, voltage distortion limits. If your system is connected less than 1 kV, individual harmonic distortion should be less than 5% and total harmonic distortion should be less than 8%. If your bus voltage is between 1 kV to 69 kV, individual harmonic distortion is 3%, total harmonics is 5%, 69 to 161, 2.5%, all these things. And probably like this is what like you need to probably benchmark with the simulation. Whether you are able to meet it or not. Like we have 136% THT here versus acceptable limit of 220 kV, the acceptable limit of is 1 and 1.5 percentage. But like means also we have 136 percentage, which is means like which is not really a system to have. Like means also we need to find out what's the mitigation measures which we need to take. So just to give a quick idea, like I mean to say on the harmonics perspective, even if you're adding a small solar inverter as a part of your college campus, let's assume like you're receiving power supply from 11 kV and you have, say, example, 1 MVA distribution transformer in your college campus, right? Let's just assume like I mean sort of say it's a college campus, 1 MVA, like you have some demand. For example, 600, 800 kVA demand. And like you're putting some 500 kilowatt solar inverter. Let's do this analysis with and without solar inverters. Then we will see the results and differences. I'm just putting up some solar inverter model. So these are all something which you need to probably develop over the period. So I'm just putting about 500 kilowatt AC, 612 kilowatt DC solar plant with an inverter of like 540 kVA. Generation, it's like 543 kilowatt it's generating. So if you look at like disabling the system, so like now I have not really given any harmonics for the system. Now I have not really given any harmonics for the system. So I'm just checking all the buses, running the harmonic analysis. So there is no harmonics, 0% THD, 0% THD. That's because I have not really given any harmonics in the solar inverter. But if I am adding solar inverters, the harmonics, if I go and then probably like pick it up some library which I am picking up, but you can collect this information from the original equipment manufacturer and you can plot it. What you will get is you have 6.71 percentage voltage THD bus 5, which if you look at this graph, then like you will see how this waveform has changed from sinusoidal to something like this. Ideally, when the solar inverter is not there, this waveform is a pure sinusoidal one like this. But when the inverter is included and when it is injecting harmonics, you can see the harmonics and probably like your waveform has changed to something like this. And when your voltage waveform is like this, your other loads also will start consuming a current something similar to this, which is all probably not logical to have, right? So if that's clear, just put CC in chat. So means that this needs to be corrected. If this needs to be corrected, then like how do we correct it? Like let's probably plot the current and the branches as well. So how much percentage? Current is 87.1 percentage THD. So like what is allowed? Voltage limits they have given. Current distortion limits, I guess like they have given above. There's a table for voltage as well as there is a table for a current. Yes, there is the table for a current. So like means so you can look at like what's the acceptable percentage current and percentage voltage, and if it is more, then probably either you can change the device, or if it is inevitable and unavoidable to use this device, you can probably use harmonics filters to eliminate what's the harmonics which has been injected. You can try maybe active or passive filters. So that's one small portion on the harmonic side. Similarly, similar fashion, like you can go and probably look at performing DC current injection as well as flickers. So let me bring maybe a fourth beautiful software. Let me probably bring it as a part of a slide. Just give me a second. Yes. The slides helps you. Yeah, if you want, like you can take a snip. If you're an electrical engineer, power system engineer, Heat-Tap, Dixalink, PSCAD, PSSC, like PSCAD and PSSC already I have touched as a part of grid compliance. Heat-Tap I have touched now. Dixalink, that's another tool like which you can think of. Why these software tools are important? Maybe this might be the reason why, like, I mean, to say, softwares like Heat-Tap are important. Or probably like if you could Dixalink, right? So why it is important? Like I mean to say, there is a plenty of opportunity in the core sector for performing power system studies using softwares like Heat-Tap, Dixalink, PSCAD, and PSSC. Heat-Tap, Dixalink, PSCAD, and PSSC. And this software helps you to transform the student's career as well as the faculty's career, right? To like I mean to say in the research or even like corporate research, there are many things, right? And probably like you can look at the other simulation softwares as well, like PVSys, Homer Pro, Homer Grid. That's predominantly into like I would say renewables and the grid compliance studies. Just to give maybe few thoughts on like means I guess like I have 5 minutes and quickly introduce our organization. Why that probably changes predominantly your mindset. Power Projects, leading power system consulting organization. We have about 52 peoples. And if somebody feels like PhD is an overqualification, like 10% of our strength is PhD. Like 25% of our strength is masters in power systems or power electronics or power engineering management. As a continuous education policy, we put up peoples on higher studies, masters in power systems in Anna University, Chennai. With this 52 strength, we are able to reach out to 42 countries for providing our consulting services and cumulative capacity of more than 100 gigawatt, which we have supported globally in 42 countries with respect to the renewables. We have supported 100 gigawatt plus on performing a grid compliance studies. This is our consulting service base. And as far as our training base is concerned, like we have, like I mean to say, participants from 150 plus countries. We work on all the sectors, renewables, data centers, power plant, oil and gas, malls, offshore, process industries, sports stadiums, generation transmission planning, airports, ports, right? And just to give an idea, like when I have completed my BE in 2006, I thought of probably joining as a faculty in a college. Then, like, I have done my master's as well. And, like, I guess, like, the speaker who has introduced me, like, I mean, he's introduced me multiple times as a doctor, but unfortunately, I have started my PhD, but I couldn't complete it. But, like, I mean, to say, still the thirst on what we have to feel and we have to train the students that has not stopped. Even today, like we are spending 15% of our time on empowering the college students as a part of an intensive or webinars or seminars, etc. And like I mean to say, we have trained 28,000 industry participants in the last 3.5 years. when we have started the online training program in 2021 March, last 3.5 years, we have trained 28,000 peoples working in various industries in 150 plus different countries, and that probably becomes our training service. So if you feel like maybe one last gift which I will give you, like means to say 2 more minutes, even if you're a faculty, if you want to transform your career, if you want to transform your career to something else on the power sector, ensure that you are registering for my webinar on career enhancement. Either that will help you directly, uh, like means see you to transform your career, or that will help you to transform your student's career. That's the link is there in the chat. So that will ask you just your email ID. I don't think it's going to ask anything else. That is probably like I mean, so to say, some photos needs to be updated, but I guess like still it works. Career enhancement that's going to come on coming Sunday, that is 8th December. Register. You will ask just your name and email ID, nothing else. You will get an idea. So that session probably helps not only the engineers, even the college faculties, how they can help their students to grow in the power sector or power systems, or how to transform their career itself. And like we have left with 1 more minutes. If there's any questions, I am happy to take it up. If not, hope the session is useful. If it is useful, just put useful in chat. And if you have any questions, I'm happy to take. And maybe I can hand over the session back to the moderators or organizers. Yeah. If it is useful, if it is not useful, no worries. Put not useful in chat. Right? All right. ₹2 50 paise to ₹3 50 paise per unit of solar energy. Is it cost? Is it only generation cost? It's not a cost of generation. It's a cost at it's a price at which the generating units are selling. So which means their cost will be less. If Pepsi is selling their Pepsi bottle at 50 rupees, it's not their cost, it's a price, which means their cost is only maybe 40 rupees and they may be making 10 rupees profit. Similar patient, like when I say like 2.5 rupees, this 2.5 rupees is their selling price, which means their cost is much less than that. It doesn't really include the transmission cost. It's only like generation and probably selling at point of interconnection. Kumarasamy, I guess like that answers your question. Maybe you can probably look at some simulation softwares like PVSys, where it is, yeah, to probably understand that cost perspective of like how much cost, like if you're going for a fixed retail, single access tracker, etc. I guess like we have a video in our YouTube channel itself, probably that gives you an idea on the cost perspective as well. Where it is. If you, yeah. So grid connected and standalone solar plant design, if you go with this, I guess like this sessions will give you like quite a lot of cost perspective of solar plant. All right. Yeah, I'm done. So thank you so much for this opportunity and 90 minutes. I guess like that has added a little value to your thinking. And if you are really looking at our contact numbers or something, I would suggest you to reach out to me in LinkedIn. So that's the best possible way where I will be a bit more active. So you can reach out to me on LinkedIn rather than I'm sharing my contact numbers. Yeah, that's pretty much from my end. Thank you all. Thank you so much. Maybe organizers, you can probably take it back. I guess like I need to, in case I have to give a host or co-host list, I can probably unmute everyone and someone can probably raise a hand. I can transfer.
As we conclude this enlightening session, I take this opportunity to extend our heartfelt thanks to our esteemed resource person, Dr. S. Selvakumar, for sharing his invaluable insights and expertise with us today. His depth of knowledge and practical experience in power systems have left us inspired and enriched. I would also like to thank our institution for making this event possible. Lastly, a big thank you to all the participants for your enthusiastic involvement and keen attention. Your presence is what makes such events worthwhile. Let us carry forward the knowledge we have gained today and apply it to drive innovation and excellence in our respective fields. Thank you all and have a great day here.
Thank you.
Thank you, sir. Thank you so much. So we are running in short of time. We can start the next session. Balamurugan, sir.
Sir, good evening, sir.
Yeah, good evening, sir. Sir, welcome you for this day 4 of Atal online FDP, sir. So I call upon Jeevika to give the intro about the resource person for this session, and sir will ask sir to deliver the talk.
Thank you, sir. A very good evening to everyone. I am Jivika from Electrical and Electronics Engineering Department of Sri Krishna College of Technology. I welcome you all to the second session of day 4 of the FDP. Today, we have with us Dr. S. Balamurugan, Chairperson and Professor at the Department of Electrical and Electronics Engineering, School of Engineering, Amrita Vishwa Vidyapeetham, Coimbatore. Dr. Balamurugan is a true visionary and a dynamic leader in the field of electrical engineering and power systems. His relentless dedication to research, education, and innovation has left an indelible mark on the academic and professional communities alike. Dr. Balamurugan began his illustrious academic journey with a bachelor's in electrical and electronics engineering in 2001 and master's in power systems in 2002, both from Annamalai University, securing first class with distinction. He earned his PhD from Anna University, Chennai in 2010. Currently serving as a chairperson and professor at the Department of EEE, Amrita Vishwa Vidyapeetham, Dr. Balamurugan has over 2 decades of teaching experience. He has made remarkable contributions through 39 international journals, 70 conference presentations, and over 100 guest lectures, seminars, and keynotes across India. His research and expertise spans power system operation and control, smart grids, artificial neural networks, and gas turbine control. Dr. Balamurugan has also been instrumental in developing hardware-based power systems and guided numerous BTech, MTech, and PhD scholars in cutting-edge fields. Dr. Balamurugan's accolades include National Innovative Teacher Award presented by the Honorable Minister of HRD, Sri Prakash Javadekar. This recognition, accompanied by a cash prize and a silver medal, honors his innovative pedagogy in laboratory-based model teaching of power systems. In addition, he serves as a president of Institution Innovation Council at Amrita Vishwa Vidyapeetham and as a single point of contact for the Smart India Hackathon 2019. His dedication to fostering innovation and skill development among students is truly commendable. We're incredibly fortunate to have such an accomplished and inspiring individual with us today. I request everyone to join me in giving a warm welcome to Dr. S. Balamurugan. Sir, over to you.
Thank you, Jeevika. Thank you. Uh, Sorry, I don't have the rights to share my screen and also to switch on. Okay, I got it. Very good evening, all of you. I believe that my slide is visible and I am audible.
Yes, sir.
Thank you. Thank you. Thank you. So thank you so much for that brief introduction, right? And also giving me an opportunity to deliver a talk on the power systems on this FDP. Thank you so much for this opportunity. Um, maybe I will, before getting into my slide, I will just tell you basically what kind of work we are doing in our power systems laboratory is we are involved in the development of hardware facility. As it is mentioned in the introduction part, we are involved in the development of hardware infrastructure for the power system. Generally, we make use of software to teach power systems, but in our department, that is at Amrita School of Engineering, we are trying, we are not fully matured, but we are trying to bring more expertise into the development of hardware infrastructure to basically it is to teach the power concept of power systems, and slowly we are moving towards the research focus on the power systems, where in the recent maybe in the last 1 or 2 years we started making use of IoT applications for the power systems, and later we started using machine learning and AI techniques in decision making and also in the control of power systems. And in the last 1 year we started working on cyber security, that is what are the different security threats are there for the power systems and how we can protect it. So these kind of the aspects what we are focusing in the last maybe 3-4 years we are working on it. Generally we also develop we also put a communication and smart communication and also intelligence to the power system. That's why we started calling our power system as a smart grid. That's why I made my topic slightly something like AI, IoT, and cyber security in the smart grid, in which we are working on the past 3 years. This maybe I will just give you a general idea about what we are doing here. It may be at the different levels like UG, PG, and the PhD level. Maybe towards the end of the presentation, if you have any specific questions to take much deeper into the particular topic, I am ready to do it. So my PPT will be very generic, or it will tell you in general about what are the different verticals under the AI, IoT, and cyber security that we are working right now in our department. That is what I will just give you an idea so that it may inspire you or it may help you to take your research forward. That's the whole idea of this presentation. So I have been given about 1.5 hours time. Maybe I will try to take about 1 hour 15 minutes for my presentation. Maybe last 15 minutes I'm ready to take up your questions. So with that introduction, let me move on into my presentation. So this is the smart grid infrastructure basically we developed in our power systems lab. So whatever I told you about AI technique or IoT or cyber security, all those things you are able to implement on the real-time power systems only through this basic power module. This is a basic power system module that we are right now having in our power systems lab. This is nothing but the conventional IEEE fiber systems which is available in the literature. We have just taken that same 100 kV. Just a second. We have just taken the this is the IEEE fiber system. You can find basically the IEEE fiber system which is available in the literature. It is of 100 kV, 100 MVA. That is what is available in the literature. So what we done is to make it convenient to work in our laboratory level. So we have scaled down all the parameters. That is parameters like transmission line resistance, reactance, shunt admittance, and also load compensation. Everything we brought it down to the 400 volt 3 kVA. It is nothing but a conventional our per unit conversion. Using that basic per unit conversion, we converted all the values from 11 kV, sorry, 100 kV, 100 MVA down to 400 volt and 3 kVA. That is what we did it. So you can find a fiber system here. Bus 1 is the slack bus where we connected the electricity board, and bus 2, bus 3, bus 4, bus 5, it can be used as a PV bus or a PQ bus. You can use it in whatever way you want. We just made the generators available in the lab, so the generators can be connected in any of these 3 buses so that it will start working as a PV bus. Similarly, any loads can be connected to any of these buses, and if anybody wants to do any shunt compensation, they can connect it. So if you just look at the buses, there are 3 provisions are given. In each of the 2, 3, 4, 5, you can find 3 provisions are given. In these provisions, either a generator can be connected or a shunt compensation can be connected. So it's up to the user to convert it to a PV bus or the PQ bus. Then apart from that, in each line, you can find there are 7 lines are there, right? All the lines are connected. So it is connected by a RLC parameter where resistor and inductors are connected in series, and the capacitor, either it can be connected as a nominal T network or it can be connected as a nominal pi network, or even you can go for a short transmission model. Anything can be done. So that provision is possible. So apart from that, you can find, we have just given a small connector here. In each line, you can find a small provisions here. That provision is basically to connect any series compensation. If anybody wants to work on series compensator like TCR, TCSR, whatever they want to connect, they can make use of this provision. So this is a basic infrastructure facility what we have developed in our laboratory through the seed funding that has been given by Amrita Vishwa Vidyapeetham. Through that, we just developed this basic infrastructure. So now the IEEE fibers, and to validate it, what we do is the IEEE fiber systems, whatever answers you are getting in the ETAP simulation model, the same answer you will be getting it when you are running it in the real time. Whatever load and generator you connect it in the ETAP, and if you get the load flow results, if you connect the same generator and the load in this model, you will be getting the same answer. Maybe some small 5-10 watts of difference may be there, but it will give the same answer. That is how we validated this particular model. And that is a basic power system network. On top of the power system network, what we did is for the data acquisition, we went for two basic data acquisition system. One data acquisition system is for doing the steady state analysis. Another data acquisition system is for doing the transient analysis and the transient control. So we made our data acquisition system into two. So if you just look into this diagram, you can find there are a lot of meters are connected. These are digital meters capable of giving you the data through the communication line. So for all the 7 lines, we connected 7 digital meters, and for all the 5 buses, we connected 5 different buses. So these, for 5 different buses, we connected 5 meters, and these meters will provide you voltage, current, real power, power factor, and the frequency. These 5 informations will come from these meters. So what these meters will do is, these meters are capable of giving you the information in the Modbus protocol through RS485. So all these meters are connected together, right? We have a provision here. So through that provision, we connected all the meters in sequence through a Modbus protocol in RS485. It has been connected to the, using a RS485 to USB converter, it is connected to the Raspberry Pi. So in Raspberry Pi is going to act like a master, and all these 12 meters will act like a slave. So these Raspberry Pi will collect the information from the registry and it will display. And these meters are capable of giving you 1 data per second, and this information is for doing steady state analysis and the steady state control. And what we have done is, after pulling all this information from the meters, right, we upload that information to the ThingSpeak environment, where you can view these data in the cloud platform, that is cloud, through the ThingSpeak platform. Why we went for ThingSpeak platform is, ThingSpeak platform allows us to interface with the MATLAB. So we do lot of analysis on the acquired data directly in the MATLAB when the data is available on the cloud through the ThingSpeak platform. That's why we identified ThingSpeak platform for the data acquisition on the cloud. So this left-hand side setup is completely for the steady state analysis, and on the right side it is for the transient analysis. What we do here is, you can find we connected some sensors here. You can find some sensors on the left side, and you can find some sensors on the right side. So these sensors are voltage sensors. These sensors are the current sensors. So for all the 7 lines, we connected 7 current sensors to measure the current. And in all the buses, we connected voltage sensor. And we are having a simultaneous sampling DAC in our laboratory. The speciality about the as the name states, right, the simultaneous sampling DAC, the special thing is it will acquire the information from all the buses at the same time. right? So that you can it will work like a PMU. So PMU basically it takes the sample from any part of the power system at the same instant, and it enables you to measure the delta. And we are just trying to bring the same logic into this. That's why we identified the simultaneous sampling tag, which will collect the voltage information from all the 5 buses at the same instant, and that data will be available in the LabVIEW environment where we apply the FFT technique. When we put the FFT techniques, this gives us the voltage magnitude and the angle at all the buses. So this one, the right side one, it is capable of giving us 10 to the power of minus at the time of 10 to the power of minus 6, we are able to get one data. But whereas the data acquisition system, what we have on the left side, it is capable of giving one data per second. So this is what is the data acquisition systems, what we put on top of the power systems, and it connects the and through the communication, wireless and wired communication, we make the data available on the cloud. So this is what is the smart grid infrastructure, which is currently available in our power systems laboratory. And this has been submitted to the for the Indian patent, and the patent is also published. We are waiting for the guarantee from the Indian patent side. So this is what is the basic infrastructure. So all our IoT, AI, and data cyber security are based on this particular interface, this particular base network. So what we do, initially what we do is in all these buses, you can vary the generator, you can vary the load. So what are the different tasks that you can do in this system is you can vary the generator, you can vary the demand, you can do some lot of series compensation, you can do shunt compensation, right? You can remove a particular line. Maybe you can find there are a lot of isolators are there. By means of opening or closing this isolator, you can reconfigure this network also. This 5 bus can be converted to a 4 bus, or it can be converted to a 3 bus, or if you want, you can operate it like a 2 bus. So any reconfiguration is possible. And also you can find we just put one green color at the out end. So from any point, you can also create a short also. So creating a fault is also possible. So all these different actions has been carried out in this network with the time stamping, and those informations are collected in the ThingSpeak platform, and the data is made available on the IEEE data port. So you can find this is you can anybody whoever wants to need a data set for your normal event or fault event. If you want any data for the IEEE fiber system, the data are collected from this network, and we uploaded this information in the IEEE data port where it is available. So if anybody wants to use AI on the data, or machine learning on the data, they can make use of this information. Actually, this is a data set which is collected by undergraduate students of our department. They uploaded this information in the IEEE data port. Maybe 2 years before, they collected this information and they have uploaded. So most of our database analysis are based on this particular database. So that's about our data. Then we slowly started what is our next levels one. Now our infrastructure is ready. Then data is also available with us. So our next plan is to give some intelligence to this smart grid. So the smart grid is ready. We want to make it intelligent in the sense our major objective is to give a self-healing characteristic to smart grid. That is our major objective. That means whenever a problem comes to the power systems, it has to correct by itself. So that kind of intelligence, that is what is the self-healing thing we want to give it to this network. That is our next step. So for that, we just took multiple step-by-step action to give a complete intelligence to the smart grid. So one of that action is the cloud and edge-based control. So now the data is available. Data is available at the local level, and the data is also available at the cloud level. So we want to bring in some control here. So control, we want to establish 2 types of control here. One is cloud-based control. Another one is edge-based control. So these are the 2 controls which we want to implement on our network. So why we call it as a cloud-based control is the decision whichever has to be taken at the central level. Whatever decision that you want to take it at central level for the entire power systems, we call it like a for a cloud level. So that means the data whichever is available on the cloud, that will be used by the algorithm, and that algorithm will decide what change has to be done in which part of the power system. That algorithm will take care. That's the in those conditions we use cloud control. In some of the control we implement the edge control. That means it is independent of the network, only on the particular node, only on the particular bus we want to do some control. In all those technique we go for the edge control. For example, if you just see this application which is there on the cloud, we just used two types of application. One is cloud, another one is edge. Maybe this is a sample network what I brought it here. In this sample you can find in the cloud we wrote an algorithm for the congestion management. Yes sir. Shall I continue? Is it, am I audible?
Yes, sir. Yes, sir. Sir, a small suggestion. Sir, in your presentation, pop-up
sir.
is there. You can hide that, sir.
Oh, sorry.
It's blocking the presentation. Now it's fine, sir. Fine, sir.
Okay. Thank you. So, sorry. So we just went for two types of control. Maybe for the participants, if you have any question at any point of time, you can stop me and you can answer. You can ask me the question. I will try to give you better clarification on our setup. That I'm ready to do it. So we are going with two types of control. One is cloud control, another one is edge control. So in the cloud control, the example what we have taken is the congestion management. So maybe I will explain in detail about the congestion management in my future slide. But what basically this congestion management they do is it collect the power flow in all the line, and we write a central algorithm to relieve the congestion, and that algorithm will tell you how much power is to be varied in each bus. So that change in P, that is what is the answer which the congestion management algorithm will give. That will be directly deployed in the respective buses. So we just have a node MCU here. This node MCU will interact with the cloud, and whatever the change in power that is explained, that is expected by the congestion management algorithm, that will be deployed on the respective bus with the help of the node MCU, which do the control. And similarly for the edge control, the sample what we have taken is at any point of the bus, if you want to maintain the power factor as 0.9 or 0.7 or 0.6, you can say that in this bus I want to keep it to be 0.9. If you just send that information from cloud to the edge, in edge also we are using the same node MCU. But what this node MCU will do is, once if it receives the reference power factor from the cloud, then it will decide, the intelligence will be available with the node MCU. This will decide how much capacitor is to be connected to that particular bus. That decision will be taken by this edge, and it will connect that much capacitance to it, so that it will bring that power factor to the expected level. So this is what is one of the sample which we have developed on the IEEE fiber systems available in our laboratory. So what I am trying to convey through this particular slide is, we established two types of control. One control is at the cloud level, another control is at the edge level. So this is a small simulations, small hardware testing what we have done with it. So you can find the user will give the information to the cloud. All the information, it will come to the cloud, and the user will live monitor what is going on in the power system network. They can connect it. So similarly, from the cloud, when there is the congestion management algorithm is available in the cloud, so it will decide how much power has to be connected in, how much change in power has to be done in each bus. That decision will be taken at the cloud, and it will send the information in the Wi-Fi, and through ESP, through the ESP, that is to the node MCU, it will activate the relay. Accordingly, the change in power will happen. And you can find in the graph whatever change that is happening in the power, that will be displayed in our in a graphical format, and also in the data format in the ThingSpeak platform. These informations are just a screenshot of the ThingSpeak platform, which live monitors the IEEE fiber systems available in our laboratory. Similarly, this is the same network. Only thing is, here we just connect the relay, or we just control the relay to control the capacitor, which in turn control the power factor. You can find by means of varying the capacitor's value, we were able to control the power factor in the bus. So this power factor is also displayed in the ThingSpeak platform. But the data comes through the digital meters through Raspberry Pi. It gets connected to the cloud. So this basically, I just bring these two slides to tell how we established the cloud control and the edge control in our existing IEEE fiber system available in our laboratory. Okay, so let me just go a little bit deeper into how we deployed the congestion management algorithm. This is also whatever I'm explaining here, everything is on hardware. It is on or not on the simulation. We will try to make use of some of the intelligent technique into the hardware to get the solutions. So here, what happened is the entire IEEE fiber system information, it is collected in the cloud, where we will just check the line limit, and the compensation in each line is also possible. Control of the bus power is also possible. These are the things which is already available in the our network, which I just now explained in the previous slide. So now what we are doing is, whatever data that comes from the data collected from the actual power system, we are giving it to the genetic algorithm. So genetic algorithm, it solves one optimization problem. What is that optimization problem? It basically does, it just want to do minimum amount of change, whether it is a bus power change or the line reactance control change. We want to keep it as minimum as possible. So demand change or generation change or line reactance change, that change should be as minimum as possible. That is our objective function. With that objective function, and our constraints are the total generation at all the 5 buses plus the total demand at all the 5 buses should be same. That is our equality constraint. Then our inequality constraint is the in each bus it is having its own limit. You cannot have a wide range of real power control on each bus. So what is the limit? How much power can be varied in each bus? That is one of the inequality constraint we have used. And another inequality constraint is, in each line, how much reactance can be controlled. That is also our, in each line we just used it something like 10% plus or minus 10% for each line. Practically we are capable of changing the line reactance by 10% plus and 10% minus. Whenever we want to go for plus 10%, we go for a series inductor compensation, and whenever you want to go for reduction in the reactance, we go for series capacitor compensation. So based on that capacitor inductor value, we decide the minimum value and the maximum value. These are the physical constraint. So considering these physical inequality constraint and equality constraint, on equality constraint of generation equal to the demand, our genetic algorithm will run at the cloud, and it will decide how much change should happen in the generator, how much change should happen in the line. Everything will be decided by the genetic algorithm. And once if the decision is given by the genetic algorithm, as I explained in the previous slide, that much amount of control will be automatically deployed in the power system. That's what you can see in this right side figure. We are having a relay. By means of activating the relay, a suitable amount of power change will happen in the respective buses, which will relieve the congestion. So this is one of the application, that is self-healing applications, what we have deployed in the IEEE fiber systems. So that's a small intelligence, self-healing intelligence we have given to the hardware infrastructure which is available in our laboratory. Then you can see our previous explanation is completely on the real power, and slowly we want to do some kind of intelligence to the reactive power. So reactive power or the voltage, that is our next plan. We want to do some kind of voltage support to the network. For that, the topic what we have considered is the voltage stability enhancement. We want to improve the voltage stability of the entire IEEE fibers network. So what we have, so this is, if you just see the previous one, the control is basically based on the real power change and the line reactance control. That is what is the control variable in our previous case study. But as far as this case study is concerned, our control variables are shunt shunt reactor compensation. That is, we can connect the capacitors or inductors as a shunt model, and also we can connect a reactance in the series. So our objective is to how to enhance the voltage how to enhance the voltage profile of the entire power system. That is our whole objective. So when we talk about the entire enhancement of the voltage profile of the network, so naturally it gets into the cloud level control. So what this cloud level control it do is it collect the real-time information. Already we have a real-time information through the meters. So those real-time information, it comes to the cloud. So from the cloud, what we do is we just make use of the MATLAB. What this MATLAB it basically do is it is having an optimization algorithm. Again, we have an optimization algorithm. Here, our objective is to minimize the VSI, voltage stability index. We want to minimize this VSI value. So the formula for VSI value, which is sum of all the, which is LMN values calculated for all the line. So totally we are having 7 lines. That's why we are taking the cumulative of it. So the LMN value should be minimized. So to minimize this, the variable factors are the 7 line reactance can be controlled, and the bus 3, bus 4, bus 5, only these 3 buses we connect, we used it for the shunt reactor compensation. So those 3 also we have considered. So as I told you earlier, this line reactance can be controlled from 90% to 110%. That is what is the range we use for the line reactance. And for the shunt capacitor compensation, we use it something around 0 to 2 per unit. This is what is our optimization problem. So what the GA will do is, GA will run this optimization problem. It can be any optimization problem. So it will decide the Q value, and the calculated C value will be informed to the local edge. That edge will connect that much amount of capacitor in the respective buses, and it will enhance the total voltage stability of the grid network. So this is what the small testing we have tried it on our network on the voltage stability part at the cloud level. So you can see this is our convergence characteristics, what we get through GA, and you can find the VSA value before and after. This blue color is the voltage stability index for each line before doing this compensation, and this is what is the VSA value after doing the compensation. So we were able to improve it, and you can find this is what is the change that is done in each transmission line. There are 7 lines are there. You can find the minimum bound is also given, maximum level is also given, and the red color is the value which is recommended by the GA. And similarly, you can find the range of the reactive power in each bus 0 to 2, and this 0.2 is the value recommended by the GA. That is optimal value given by the GA. So whatever optimal value that comes from the GA, that is automatically deployed in the network using the edge control. And this is what is the VSA value which I explained in the previous slide. The VSA value which is computed before and after the deployment of this particular self-healing control. So now you can understand that the network what we have the basic power system, and on top of it we have a data collection system, and the data it goes to the cloud through the communication, and we were able to do cloud control, and also we were able to do edge control. And some of the small applications what we have done is we were able to do the that is congestion management we were able to achieve, and also we were able to achieve the voltage stability index. These are the small things we have done on this, and our next target was to do the relay coordination. That is our next task. So here what we do is, so you can find there are lot of there are 7 lines are there. So what we do in this is, in each of the line we are just connecting a small edge level. This is a edge level relay. We are connecting it in each line at both the sides. Since it is a loop network, in each of the line we are just connecting 2 numerical relay on both the ends of the transmission line. So this communicates with the central cloud. What this edge relay will do is, inside this we will be having the IEC characteristics, and the IEC character. Yes, sir. Okay. So whatever you can see in the small blue color box, that is what we have given here.
Excuse me, sir.
Yes, sir.
Sir, what sort of cloud type you will be doing here, sir?
You are asking about the cloud. What cloud we are
Yeah,
using?
yes, sir.
Ma'am, the ThinkSpeak cloud is available. No, initially we started with the free version, which is available in ThinkSpeak. That is what we
ThinkSpeak.
have used. ThinkSpeak.
Oh, okay. Okay. We can't do it in AWS or OpenStack
You
like
can
that.
definitely do it. You can definitely do that.
Uh,
But why? The reason why we went for the ThinkSpeak platform is we are more comfortable to work with the MATLAB. And
oh.
ThinkSpeak, it has the natural connection with the MATLAB. You can
Uh,
run the program in the MATLAB, which is capable of taking the data from the ThinkSpeak platform, and it will give you the result. That's the reason why we chose the.
It's a open source, sir.
It's an open source, but the problem with the open source is the open source ThinkSpeak platform will give you only one data per 15 seconds.
Yeah. It's
If you are
slow,
okay
no?
with the
That's
one
why I'm
data for
asking it.
every 15 seconds, if you are for every 15 seconds, if you are okay with single data, then you can definitely go for ThinkSpeak platform. It will give you appreciable results. But if you want it to be very fast, then you have to buy.
Why can't you use it in OpenStack, sir? Is it possible?
Yes, it is possible. You can do it,
But
but
in that also we'll be having a one data and all.
yes, you can do that. You can do that.
It will be having multiple data. We can take it in OpenStack, no, sir?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Oh, okay. Thank you, sir.
Okay. The reason why we went for it is since we are we are handicapped to MATLAB. That's the reason why we identified the cloud, which allows me to work on the data in the MATLAB environment, and it is available for free. So far, whatever analysis I have talked to you, everything is only on the steady state. So for the steady state analysis, your all our controls are steady state control. So in that case, your one data for every 15 seconds is more than enough.
Thank you, sir. Thank you.
Thank you. So coming back to this, so whatever this blue color you are seeing here, the same blue color, that is what is given here. Only thing is this is a small edge control. In this edge control, the small component what we have is that IEC characteristics is available in this particular relay. So what we will do is all the power system information is already available in the cloud. So the cloud will decide what should be the TMS value and the plug setting value, that is plug setting and time setting of this relay for that IEC characteristics for each, that will be decided in the cloud, and that information, only the TMS information and the plug setting information will come from the cloud to this particular edge. And so now this relay is capable of working on the characteristics as you expect. So whenever the current in this line, when it goes, when it crosses the threshold of that IP, and it will open the circuit breaker, which is already available in the line. So it will automatically open it. Only thing is the IP value and the TMS value, which we put it in this particular network inside this edge, it ensures the relay coordination. So it is having two functions. One function is whenever the current goes beyond the threshold value, it should open the circuit breaker. That is one function. Another one function is it should also do the relay coordination. That means whenever the primary fails, then the backup should work. So keeping this relay coordination and the protection, this setup has been deployed into the IEEE fibers network. What we have developed in our laboratory, and this development is not completely fulfilled. We are about to complete it. Hopefully in another 2-3 months we will be having the full network, but we tested it at the smaller level, not at the 7-line network. We didn't do it, but we were able to do it on a single loop. Multi-loop, we are working on it. So now my PhD scholar is actually working on it. So this here also we can use any optimization problem. Here our objective function is the primary protection and the backup protection. The total time taken for the primary protection and the backup protection that I want to minimize this. That is our objective function. And the time of operation, the standard inverse curve is considered to be the equation of the relay. And the coordination time, that is the backup time and the backup time and the primary time, we consider it to be 0.3 seconds. And the TMS setting, the minimum value and the maximum value are considered to be the inequality constraint, and the another inequality constraint is the fault current. So one that is 125% of the load current and 2/3 of the minimum fault current. That is what is considered to be the minimum and the maximum limit for the fault current on each line. So considering this constraint, considering this objective function, we were able to achieve the time setting. We were able to achieve the time setting and the current setting of the each relay in the network. So once if that is decided, automatically the cloud will transfer the TMS value. The cloud will transfer the TMS value and the IP value to this edge, and the edge is ready to function. So whenever the network gets changed, automatically the time setting and the plug setting will automatically get updated, and it will be ready to protect, and also it will be ready to do the coordination also. So if you just see, we have completed the real power control. Then we were able to do the reactive power and the voltage control. Then at the level 3, we were able to do the some kind of protection also we were able to do. Next thing what we did is we thought of doing some cyber security aspect into it. So for the cyber security aspect, our cyber security aspect is having two things. One is we just tried it with the conventional two-area network. Most of you will be very much aware of the two-area network. So we just first started our cyber security protection on the two-area network, and after that we are expanding it to our fiber system also. Now we are trying to include the cyber security aspect into the IEEE fiber system. Maybe first I will explain you how we have deployed the cyber security aspect on the two-area system. Then I have my research scholar with me right now, so he will be explaining about how we are deploying the cyber security on the existing fibers network, which you have seen right now. So what we did in this area one is, this is our conventional two-area network, so most of you will be aware of it. But only thing is, what we did is we just pushed all the data to the ThingSpeak. Everything will not happen automatically. So the area 1, we just wrote the state space equation of the area 1, so that it will give you only the del F value. The del F value will get into the same area for the area control error to give an input to the PA controller. Similarly, for the state space model of the area 2 is also written, so that the del F2 will come out of it and it will decide the area control error. And this frequency and the area 1 frequency will get into the this del F1 information will get into the ThingSpeak platform. This del F2 from area 2 will also get into the ThingSpeak platform. From this del F1 and del F2, using the state space equation of the tie line power, del P tie will also get into the ThingSpeak platform. So the ThingSpeak platform, it calculates the that is the cloud, it calculates the area control error, which is nothing but the del F1 plus del F2 plus del P tie, which is computed here, and this will go to each area. So area 1 will receive the area control error. Area 2 will also control the area control error. So you can find, we just developed the entire two-area system within the system with the cloud connection. So why we brought in the cloud to calculate the area control error is, so now it is vulnerable to attack. You can attack the information comes from area 1, which is del F1. The information comes from maybe area 1, something like Tamil Nadu, where the del F1 information comes to the control center, and from the area 2 is something like Kerala, where the del F2 information comes to the control center, and the power flowing from Tamil Nadu to Kerala is coming to the cloud, which is nothing but a control center. Now the attackers can attack this control parameter. So if they attack this control parameter, then the entire function of area 1 and area 2 will be in threat. So what we do here is we just created 3 types of attack on this. Those attacks are random attack, scaling attack, and the ramp attack. So these 3 attacks, we do it on the del F1, we do it on the del F2, we do it on the del Phi tie, and we just see what kind of impact it creates on the frequency 1 error, area 2 frequency, and also in the tie line power, what impact it creates for the different types of random attack and the random attack, then ramp attack, step attack. So these 3 attacks, how it responds, that is what we listed here. And this entire data set is also made available in the IEEE data port. So whatever data port, it is done by one set of my BTech students in the last year. So for the different types of attack, for all the three attacks, at Del F1 level or Del F2 level or at Del P TIE level, how that is for scaling, ramp and the random attack, how the system it behaves, the entire data set is right now available in the IEEE data port. And what we did with the data is we just used some different, this is actually a practical system. It is not a simulation system. The entire state space model of the area one is written as a x dot is equal to ax plus bu. In that format, it is written inside the ESP32. Similarly, for the area 2, the 4x4 matrix x dot is equal to ax plus bu, that is also written in the ESP32. Similarly, another ESP2 is taken where the equation for the tie line, which is 2 pi t by s, that is taken inside the another ESP2. So whatever data we have given, it is not a simulation model, it is the hardware model. So this interface through the cloud platform, it interface. So on top of it, what we did is we were using the data, we were trying to identify what kind of attack has happened, whether we were able to identify it or not. That for that we used different technique. One is support vector classifier, then adaptive boosting with extra digits we used, and the PCA with adaptive boosting. These three techniques we used just to check whether our data is working or not. So we just inject different false data, and we just confirm that our machine learning can be able to identify an attack on the two area. This is only the starting for our cyber attack part. But whatever the IEEE fiber systems I have shown you on my previous slides, on that we are involved in the serious cyber threats we are doing on it. Maybe in another 5-10 minutes of time, my research scholar will explain you about how we are trying to deploy it in our IEEE fibers network. So we completed the real control, then voltage control, then the relay coordination, then cyber security. Next, we are moving on to the deregulation. So we want our power system, that IEEE fiber system, not to be the in the vertical environment or the conventional environment. We wanted to work on the deregulated environment. So that what we did is for each bus we just connected a ESP32. You can find in each bus, earlier we had only the meter. Now we connected a ESP32 in each bus. What this ESP32 will do is, ESP32, this is what is going to work with the power pool. So any bids and offer for that particular bus, it can be a supplier or it can be a consumer. So they will provide the bids and offer. You can find this red color. It's a bids and offer that will be given. Bids and offer which will be given to the ThingSpeak environment. So offers will be given by the generating company to the central power pool. Here we use the ThingSpeak environment, and all the demand, that is distribution company, they send the bids to the central power pool. And what the central power pool will do is they will calculate the MCP. You can find all the information will come there. So in the cloud, they will put this thing, that is they will find out the crossover point, and they will decide how much power is winning and what is the cost for it. And that amount of power, how much power is for the each bus, it will be calculated in the cloud, in the ThingSpeak platform, and that information will be given back to the respective ESP32. You can find the power pool is giving back what is your winning power and at what cost you are getting the power. So those informations, that is MCP information, will go to the respective ESP32. So this ESP32, as I told in my previous slide, so based on whatever number it comes from here, only that much power it will allow to consume in each of the buses. That will be taken care by the ESP32. So now you can find that our system is having a deregulation flavor. That is, it is capable of doing some kind of bidding and offer, and the market decides how much power can be connected in each of the buses. Then in this, this is a daily load curve. It is another sample what we tried. You can find these red colors are nothing but in those duration there is a congestion in the transmission line. So what we did is, you can find our line 5 is getting congested. Again, we have gone to the we just tried with many optimization tool, but I am presenting only the genetic algorithm. So this any optimization algorithm will decide how to relieve this congestion in the deregulated environment, and how much power change should happen in each bus, that will decide. And when we deploy it in the buses, we were able to relieve the congestion. So what this particular slide I am trying to convey is, we were able to add a deregulation flavor, a market layer on top of the power line. So now you can find that we are having a power line. There is a data acquisition layer. There is a communication layer. On top of it, there is a cloud layer. On the cloud, we are having a real power control. We are having a reactive power control. We are able to do relay coordination. Now we added a market layer also. So that is the hardware network right now we are having in our laboratory. Then, as I told you in the previous slide, based on the result, based on the MCP, the power flow is happening. But this power pool is not giving only the power, it is also giving me the tariff, at what price the power is being sold, or what price we are buying the power. That information, it also comes from the power pool. So we want to calculate that tariff. So for the tariff calculation, we just made a very small infrastructure adding to it to calculate the tariff. That tariff calculation is based on two things. The tariff is calculated using the ABT technique and also the deviation settlement mechanism technique. These two formulas are used in calculating the tariff. So we just consider some suppliers and the buyers, and all the suppliers and buyers are connected to the ESP32 with the CTPT. And these ESP32s are nothing but they are going to give the bids and offer to the central pool, right? They maybe due to our restrictions, we didn't measure the frequency. We took the frequency directly from the SRLDC. SRLDC, that's one way of getting the frequency. So we just collected the frequency information from the SRLDC, and this ESP32 is connected in a Wi-Fi network through the power pool, which is also another ESP32. So these people communicate with each other. They supply the bits and offer, and what the power pool will do is it will calculate the MCP, and the result it will send it back to the ESP32, local ESP32, which will calculate the actual power, penalty, cost for deviation, and also the total cost based on the availability based tariff and the deviation settlement mechanism. And these information it will make available to the cloud platform, so that any consumer, if they just put their customer ID, they can see what is your actual cost. And the same information is also made available in the app using a Blink app. We just developed a app in the same information, whatever is available in the cloud, that can be displayed in the app also. It is just to show the tariff on the app platform. So this is what the same thing. The hardware began that tariff calculation. So this is what is the tariff layer we just added into the network. Maybe let me move on to the last part, which is how we are trying to establish the cyber security aspects into our existing IEEE fibers network. So along with me, we have Mr. M. Nakiran. He's working in our power systems lab. Basically, he's a computer science expert and also a power system network expert. He's trying to put some kind of machine learning and AI technique on the cyber security. So he's not only he was a research faculty of our department. Currently, he's working as a full-time faculty in our department. So I request Nakiran to explain what plan he's having, or how he is executing the cyber security aspects into the existing IEEE fiber systems. So over to Nakiran.
So good evening to all. And first of all, I thank my HOD for giving me opportunity to deliver this lecture to you all. And my research work is on the data analytics in the smart grid cyber security. Here I am going to give you some idea about how the power system attack classification is done in the industrial control systems of Industry 4.0. And this is the outline I'm going to describe about in this session. The technical and scientific challenge that is we are addressing in the current Indian power sector of smart grid cybersecurity, and the technical and scientific details of the wide area monitoring, protection, and control system (WAMP systems) is generally as a smart grid. and data analytics through machine learning support for cyber attack classifications, and my proposed solution for this smart grid cybersecurity, and what can be the future scope of work in the smart grid 5.0. So you can see the technical and scientific challenge in the smart grid cybersecurity. In the upcoming years, by 2030, the Indian power sector, the demand of 500 gigawatt of power from the renewable energy, which needs a effective monitoring, control, and protection operation from the remote location. So along with this existing power grid, which might require the bidirectional communication to take the control of the operations. So the conventional, our Indian power grid are using the SCADA-based system with the IEC 6087-5 standard communication protocol at the substation level, which lacks in synchronized timestamp at the different geographical location. And from the 2014 to have start to till date, our Indian grid systems are getting converted into the smart grid and making the with the motto of one grid and one frequency. So from 2014 onwards, our Indian power sector have got deploying with the phaser measurement unit at the transmission line, which is used to deployed at the substation level, which uses IEEE 37.118.2 is a synchronous time-stamped protocol, which is capable of getting the samples from 30 to 60 and even to 120 samples per second we can able to get. So these data are getting pushed into the phaser data concentrator at the state dispatch level center and also to the regional center and to the national center, and through the L3 layer 3 switch for the easy monitoring, protection, and control. So here you can see the difference between the sampling rate done when using the SCADA, when using the PMU. Where the conventional grid where we using the SCADA can able to sample only one sample per second every 2 to 10 seconds. Whereas the recent years, our Indian grid systems are using the phaser measurement unit instead of the SCADA, where it can able to capture the samples of 30 to 60 and even to 120 samples per second we can able to capture. So why these samples per second is required, in the sense we need to have whether there is any anomaly has been happened in the critical systems. We can't able to go with one sample per second for every 2 to 10 seconds. So we need at least, as per the Nyquist theorem, we required at least 120 samples per second to have to detect the anomaly. And this is a cyber security issues that is pertaining in the current scenario, not only in the Indian thing and all over the world, where if there is a bidirectional communication or even there is a unidirectional communication, there is a issue in the wide area monitoring, protection, and control system. And this problem should be addressed through our machine learning techniques. Right. So here I will be showing you the sample of IEEE N-bus system. You can take that can be the IEEE 3-bus system to 5-bus system or to N-bus system. And this diagram already our HOD have shown you the real IEEE 5-bus system or scaled down model. And I have worked out the algorithm basis. I have worked out taken the data set from the public source data set with IEEE 3-bus system. And considering this scenario, the thing is that each bus will be connected to each PMU phaser measurement unit, which can be able to capture 29 features. So this will be applicable to the 3-phase system, where we'll be having the voltage, current, and then a corresponding magnitude and phase angle with the impedance relay. So here the PMU is a distance-based relay. So we will be having around 29 features from each of the PMU. So as per the PMU, it is able to capture 120 samples per second with the time synchronized clock. It's a GPS clock. So it can able to sample with 120 samples per second. And these samples are pushed into to the phaser data concentrator, where you will be having in the state level dispatch center onto the super PDC with the regional dispatch center through L3 switch. So it's a layer 3 switch where the protocol used is a C37.118 is a synchrophasor communication protocol from PMU to PDC. Here I have shown you the direction is of unidirectional. Even though it is a unidirectional, there is a possibility of attack that can be established in the network layer. Network layer. Either the attacker can be as of two types. Either it may be the external attacker, or maybe the attacker may be the insider one who knows the networks. So through the Wireshark and EtherCap kind of tools with Kali Linux is one of the familiar tools for penetration testing, and also to make the attack on that. They can have the potential attacks on this wide area monitoring protection control system. With the possible attack scenarios can be data falsification or injection attack can be happened by capturing the packet, or maybe data replay attack. That means we are blocking the data and we are making the same data to be get from the attacker to the PDC, or denial of service attack. That is, we are blocking the data from any one of the PMU, or man in the middle attack. So you will be able to monitor the data and you can do any kind of manipulation over there. So these are the possible attack scenarios that can be established in the current smart grid 4.0, where the cyber attack scenarios are yet to be addressed and should be given the solution. And we have a proposed solution of statistical approach with the machine learning techniques with the intelligent ideas to be placed in the phaser data concentrator, where it can able to respond the activities within 0.23 millisecond, which is less than the 8.3 milliseconds for the 50 to 60 Hz systems. So we have considered, as I told, we have considered the data set from the public data set to work on the similar scenario, and we able to, our role is to have the ultimate aim to avoid the blackouts. So I think you might know the blackouts that have been happened in 2015-16 at the Ukraine attack on the Chernobyl power plant from the Russian attackers. And that's happened there. It happened the cascading failure also that makes the physical supportage and economic loss. Around 2.3 million people have got affected, and there is a back-to-back attack happened with 15 and also 16. So these kind of scenarios can be applicable to the Indian scenario, but even it is a unidirectional, it can be happened. If there is a bidirectional scenario, phaser data concentrator can communicate with another more protocol called DNP3. It's a distributed network protocol where we can able to control the PMU through PDC. So even there is a bidirectional communication protocol, the attacker intruder can come into the picture and make a circuit breaker relay to be tripped out and the circuit breaker to be open. So in both the bidirectional and unidirectional scenario, the attacker can be the most threat to us to make the system stability to go down. So in order to have the system to be get stabilized, my machine learning algorithm can able to respond the activities, whether the data is of normal data or the attack data, or the normal in the attack itself, whether we can able to make that whether it is a natural event or a attack event. That is, in normal event, in normal scenario itself, we'll be having a natural calamity. Due to natural calamity, the things will make the disturbance in the power flow. So even the attacker can simulate the similar kind of natural calamity due to lightning problem or maybe raining problem, this kind of things. He may inject a false data injection attack similar to a natural scenario, whereas our algorithm can able to distinguish that kind of scenario also. So our algorithm can able to distinguish between the binary scenario and also can be the triple class scenarios. And this is our proposed solution, where we are incorporating the machine learning algorithm of neighborhood component analysis. This algorithm has been already available in the scikit-learn, where it uses the principal component analysis. So what is the ultimate aim of the principal component analysis? In this, the one per PMU will be having 29 features, and we are taking for n number of systems, we'll be having n number of features. So it requires so much computation time to have the prediction and to respond to the system within millisecond. So we try to reduce the features into feature extraction technique, where NCA, neighborhood components analysis, as the algorithm of PCA with KNN. So with this, we try to optimize this algorithm with bagging and boosting techniques of extra tree classifier with AdaBoost, such that our algorithm can able to process each and individual scenarios, and we can able to respond within 0.23 millisecond to distinguish whether it is a attack or the natural event, whatever maybe. So, our ultimate aim can have achieved with the goal of earlier attack detection and discrimination and reducing the missing rate. So you may, if you are familiar with the confusion matrix of the classification problem, even false positive, if there is a false positive, it will panic the system administrator. Even there is no attack, there may be a false positive will panic, will make the disturbance of the system admin. Whereas false negative will make the there will not be no knowledge of the system administrator. The false negative case will make the system to be completely demolished. So it will have the physical sabotage. You don't have get idea. So my aim is to reduce the missing rate and also to respond within the milliseconds. So this will be our solution will be applied to this advanced cybersecurity also, and my problem can be applied to the scalability issue from 3 bus to n bus. My algorithm can be applicable, and this ultimate aim to prevent the blackouts. So what is that happened in 15-16 in Ukraine? So we should not have in our Indian grid scenario. So my ultimate aim to overcome these blackouts and cascading failure. And for the software solution, I took the dataset from the Tommy's Morris. It's an industrial control system open source dataset. It is very just a similar look like what is explained in the wide area monitoring protection control system. And we are having the test bed with the power system lab with the IEEE scaled down model of 5-bus system. And we are planning to deploy a real phasor measurement unit and real phasor data concentrator similar to a digital substation we tried to establish. And I'm going to apply my research algorithm over the phasor data concentrator through the research license. And we try to prove this our grid test bed is right enough to withstand all the cybersecurity issues. And we have published this work in our in the MDPI journal with the energies. And you can see on the title with the mitigating missing rate and earlier cyber attack discrimination using optimal statistical approach with the machine learning techniques in the smart grid. And this one Q1 publication, and the same base works. Before doing this work, I have did a base work, and with the technique of the PCA, and we try to reduce the dimensionality and produce the with a better result. And with the same reducing the computation time and also response time. And we have national journal publication published in the Power Research Journal of CPR, Central Power Research Institute in the Bangalore. So our algorithms have got approved from the national journal level and also from the international journal levels. And for as an audience, we'll be giving some input for the takeaway, where you can apply for the smart grid 5.0 scenarios, where the ML techniques like explainable AI can able to drive the decisions or transparent and interpretable and aligned with the human values. It's a human-centric decision making, where the features what is selected by the algorithm. There are some algorithms available in the explainable AI with the Lime and SHAP, and there are different algorithms that have been available in explainable AI. So explainable AI will tell you the features, what features it has been got selected by this algorithm, and this can be transparent and can be interpretable by the human-centric decisions. So the upcoming industry 5.0 will have the transparent thing and also human-centric decision making kind of things, and you can have this trust and you can have this collaboration. And another more AI techniques that can be applicable to the smart grid 5.0 is responsible AI. So here in this case of the power outage, that may be due to a cyber attack scenario or maybe some reasons for economical load dispatch, or they want to shut down some power outage. So responsible AI ensure equal power distribution by prioritizing the critical services, like hospital need 24/7. Right. So this will give you the economical load dispatch among the zone wise, where it will be giving the priority to the critical services, and it will have the balancing of the load things, so that it also maintain the grid resilience. So what does the human intervenes here? In this sense, humans remain accountable for the AI driven decisions and ensuring the oversight and control. And there are a lot of new techniques are also come into picture with 5.0, with LLM model, with the large language model. They have been getting into use, and they try to have the economical load dispatch and forecasting with the large language model. Like you might be familiar with this ChatGPT, these kind of things. So these are you takeaway you can take from this session. Thank you. Any questions? Please let me know. I can answer for that.
Thank you so much for your wonderful presentation, sir.
Yes, sir. Thank you.
Yes. And participants, if you have queries, you can turn on your mic and post your queries. And sir, I am turning on your host activity, sir. Dear participants, if you have any queries, you can turn on your mic, or else you can please post the queries on a chat box. Okay. Sir, thank you so much for your wonderful presentation, sir. I hope the presentation is very useful and informative, and we have take away many things on smart grids informations, and which we can be able to employ in the in future projects of students. And now I call upon GVK for giving a vote of thanks for our resource persons today. Jivika? Okay, sir. I think Jivika is facing some technical issues.
Okay.
Yes, sir. Thank you so much for your wonderful presentation today, sir. We hope all the participants have enjoyed your session, and we feel good for interacting with you today on 4th day of ATAL
Yes.
program, sir. Thank you so much, sir.
Yes, sir.
Yes.
Thanks a lot, sir. Thank you.
Thank you
Thank you
so much, sir. Thank you. And dear participants, in the chat box, the feedback link has been shared. You please fill the chat. You can find the feedback link, and please fill it before 10 a.m. tomorrow. And hope we will be connected tomorrow sharply by 6 p.m. Thank you all, and good night. Sir, thank you and good night, sir.
Thank you, sir. Thank you. Thank you a lot. Good night.
Yes, sir.